Welcome to part 6 of sequences and series and the last of the advanced section. So in part 6 we're looking at the limiting sum of an infinite geometric series. What a title. So let's start with a geometric series that looks like this. We've got a starting value of 2 and a common ratio of 2. Each term is double the term before it. So we can see that as we progress throughout this series, the terms themselves become really large, and so therefore the sum of the whole thing gets really large. In fact, if this is an infinite series, the sum will be infinite. And so we say that these series diverge, or that this is a divergent series. But there are other geometric series where the sum doesn't increase greatly after the first few terms. Take this one for example. We start with 8 and we have a common ratio of a half. Each time we move along, we are halving to get our next term. The sum here doesn't actually go off to infinity, but rather approaches a constant value. And so we say that these series converge. That is, they have a limiting sum that we also sometimes call the sum to infinity. Before we get into the formula for the sum to infinity, let's have a look at an example now where we can see how a convergent series approaches a constant value. First, we'll look at the sum of the first 10 terms, and then we'll look at the sum of the first 20 terms. So here's our example written out properly. Like I said, we're going 10 terms and 20 terms, so we'll do it in 2 sections, and here is our limiting sum. 2 plus 1 plus a half plus a quarter and so on. So let's write out the values that we know. Our first term is 2, and our common ratio we can see is a half. And we are after the sum of 10 terms, so we are going to use the sum formula. Now because r is less than 1, let's use this version. So, sum of the first 10 terms. Substituting in our values, we get 1 minus a half to the power of 10. That's on the top with the 2 out the front, and we have 1 minus a half on the bottom. When we plug all of this into the calculator, we find that we get 3.9961 and so on, and we'll just leave it at 4 decimal places. But what about if we evaluate the sum of the first 20 terms? So we set up the same formula, but instead of n equals 10, we're now plugging in n equals 20. Sorry about that one. Once again, when we evaluate this using our calculator, we get 4.0000 and so on. We'll stop it there. And so I think it's quite clear to tell that we're approaching the constant value of 4. And so this example has really clearly shown us how some of these series, as we move through the terms, the sum does not increase greatly. Like we started with 2 and then 1, so the first 2 terms give us 3. By the time we got to the first 10 terms, the sum was only up to 3.9961, and then the next 10 terms on top of that only took us up to 4. Alright, so now that we've done this sort of practical example, let's look at this in a more general sense. So at the start we talked about divergent and convergent, and only geometric series with a common ratio that is less than 1, or that is the absolute value of the common ratio is less than 1, only these will have a limiting sum, right? If the common ratio is greater than 1, then that's where we get a divergent series and it just goes off to infinity. So if we focus on the sum formula that we just used for when the common ratio is less than 1, and we think about going off to infinity, a limit as such. So as the number of terms, n, approaches infinity, what happens? Well, because r is a fraction, any fraction, when we multiply it by itself, it just gets smaller and smaller. And so as we take a fraction and raise it to bigger and bigger powers, this value, r to the power of n, is just going to approach 0. Okay, now notice once again that this is for r values, absolute value of r that's less than 1, or remember we can say that r lies between -1 and 1. Okay, so if we take r to the power of n to go to 0, or another way of writing that is that the limit as n approaches infinity of r to the n is equal to 0, then what's going to happen with our formula? Well, since this just goes to 0, all we are left with is a on top of the fraction. And so our official formula is the sum to infinity is a over 1 minus r. Pretty nice, hey? So let's do some more examples now using this new formula. And our first example is just confirming what we looked at before. Find the limiting sum of this series, where a equals 2, the common ratio equals 1/2. And remember, that's all we need to know when we're looking at the sum to infinity. So the sum to infinity equals a over 1 minus r, which is 2 over 1 minus 1/2. 1 minus a half is just a half, and how many halves are there in 2? There are 4. So that is our sum to infinity, or our limiting sum. Second example. Find the sum to infinity of the series 6 plus 2 plus 2/3 and so on. So we can see our starting term is a equals 6, and our common ratio is 1/3. We're dividing each term by 3 to get the next term. So we have got a common ratio that's less than 1, so that's good. So we can apply our sum to infinity formula, which is a over 1 minus r, so 6 over 1 minus 1/3. That's 6 over 2/3, and when we apply our times and flip, we get 6 times by 3 on 2. So 6 times by 1.5 essentially is 9. And so this series has a limiting sum of 9. Okay, one more example and then we're done. Does 3/4 plus 15 over 16 plus 1 and 11/64 and so on, does this series have a limiting sum? So for a limiting sum, right, we need to show that the ratio, or the absolute value of the ratio, is less than 1. Okay, that's what we need to show for a limiting sum. So let's work out what the common ratio is for this series. And to do that, we need to look at the terms. Okay, so the common ratio is one given term, so I'll start with the 15 over 16, divided by the term before it. Okay, using our times and flip, this becomes the following, and this simplifies nicely. We can see that the 4 and the 16 cancel, and likewise the 3 and the 15 cancel nicely to give us 5 over 4. Now this is greater than 1, isn't it? This is greater than 1. So therefore, this is actually a divergent series. Okay, this does not have a limiting sum. Only those series that have a common ratio less than 1 have a limiting sum. Alright, that finishes off our last example. Okay, good luck with the exercise questions.